Hey everybody. Oh, so good to see you. Hope that you're doing well. And this week, what we're going to do is learn about bond energies and what we can do with them. We're going to talk about bond breaking and forming. We'll define those bond energies. And really, this week, you have to be able to solve some math problems where we use bond energies to approximate or determine the change in enthalpy. Couple of key things for this week. Hey, when you look at the work that I'm handing out for you this week, right here where it says bond energy Pogel, and right here where it's linked, I'm basically going to go through this in the video. This bond energy Pogel that's available for you to see. If you have a piece of paper and you follow along with this video and you look at this over, you're going to understand everything you need to do for this. We're going to use these bond energies a lot. So please, please, please understand that follow along with this Pogel and you'll be successful. Let's go back to talking about bond energies. One thing you want to think about with chemical reactions, a lot like playing with Legos. You got to break things apart, and you always have this big pile of Legos sitting around at some point. But this big pile can be turned into magical things like a castle. It always takes energy for you to separate these things. You always have to put in energy to break old bonds. And when we put energy in, is that endothermic or exothermic? And when we snap these together, energy comes out. And when energy comes out, is that endothermic or exothermic? And what we can do is imagine a process where we take a molecule, break it apart into its individual atoms, and put it into a new arrangement. We can imagine that. That's probably not really how it happens, but it's cool. And with the bond energies, we can make approximations. You're going to see this in the Pogel. Which side is broken and which side is forming bonds? Take a look at A and take a look at B, E, A and E. And when you see that, you can see one side is breaking bonds. And notice what the energy change. Is it endothermic or exothermic? Breaking bonds. Is it endothermic or exothermic? Look at the sign, and that'll tell you. Look at E, and we can see right here we are making bonds, and we can see that that is negative, which means exothermic. And so you want to make sure you understand breaking bonds is always going to be endothermic, and forming bonds is exothermic. And look at this PCl3. This PCl3 that we have right here, this is the molecule PCl3. This is its Lewis structure. And what we can see in PCl3, there's 1, 2, 3 bonds that are breaking. And to break 1, 2, 3 bonds takes this much energy. To break 5 bonds takes this much energy. I wonder if to break one bond, we can figure out how much energy it would take. That's what bond energies are, and that's what we'll look at. This table that you'll see in the Pogel is all about bond energy. So bond energy is the energy required to break 1 mole of bond, so to break one bond. It's always endothermic, so the numbers that you see here are always given in a positive form. But remember, making bonds, putting things together, is just the opposite. It's equal and opposite. That's what Hess's law taught us. And so if I was going to bond one H to one H, I would see that this positive 432 would turn into negative 432. So when I make bonds, it's endothermic. When I break bond, it's exothermic. And all I have to do is know to change the sign. So what we're going to imagine, and what they imagine in the Pogel, is that the reaction occurs by all the reactants decomposing into the elements in their natural state and recombining to form the product. So in this important Haber process reaction, where nitrogen and hydrogen react to form ammonia, what we want to do is imagine a step where, what if, and this isn't really how it happens, but what if everything just broke apart into atoms, 2 nitrogen atoms, 6 hydrogen atoms. And then those 2 nitrogen atoms and 6 hydrogen atoms, like Legos, could click into a new arrangement of 2NH3. We can use this bond energy to figure that out. We can just figure out how much energy to break this bond, how much energy to break 3 moles of that bond, and what we can do then is figure out how much energy to make 6 NH3 bonds, because there's 2 NH3s and 3 bonds in each NH3. We can take the endothermic, the exothermic, and then using Hess's law, just kind of subtract them and find out what the enthalpy is. So that's what we're going to do. Let me do an example problem and get you to do a lot of example problems. In this chemical reaction, hydrogen and oxygen are forming water. What we have to do in order to count the bonds is maybe think in Lewis structures, because 2H2 could be represented right here as 2H2s. 1O2, there's a double bond inside of there, and 2H2Os, there's one, there's two. So what do we think? We need to figure out how much energy is in this bond, plus how much energy is in this bond, plus how much energy is in this bond, and add it all up. That'll tell us how much energy it takes to get up to here. Then what we have to do is subtract the amount of energy to form these 1, 2, 3, 4 bonds. And what we'll do is figure out how much energy it takes to go from here to here. And if we take this minus this, we'll get the total estimate, approximation for enthalpy. It'll kind of look like this. We'll take the total bond energies of the reactants, the bonds that are broken, and we're going to subtract the bonds that are formed, right? So it's basically the bond energy of the reactants minus the bond energy of the products. Here are my reactants, here are my products, and there are my bond energies that I see for these three types of bonds. The 2H2 would be for H, 432, 2 times 432. There is 1O2, and that's a 494, 1 times 494. And then all I'm going to do is subtract the 1, 2, 3, 4, 4 times 464, and I'm going to get this number right here, negative 498. And that would be how I can use bond energies to approximate enthalpy, changes in enthalpy. Now, in your POGIL, there's an example problem, 20 to 22, and it involves this chemical reaction. You're asked to balance it first, and then you're asked to imagine that, this breaks apart into carbon and 4 hydrogens, this breaks apart into 4 oxygens, and then this breaks down into this forms CO2 and this forms water. You need to think about all those steps and think about how many bonds are broken, how many bonds are formed. For these problems, you can either do them with the POGIL, but I want to tell you that I put out a Google form, and Google form is going to be right here, this practice form. I'm going to put it in Classroom, and this is what it's titled. It's going to be titled The Enthalpy of CH4 and CH2. And when you get to it, you're going to see, after you enter some information, I'll give you the Lewis structures. Here are the bond energies, here's the balanced chemical reaction, and here are the Lewis structures. And what I need you to do is 1, 2, 3. Calculate the bond energies of all the bonds in the that are breaking in there in the reactants. Calculate the bond energies in the products, how much it formed, and then take 1 minus 2 and get your answer. Show you that. I'd love for you to practice this. There's another problem to practice on this. You can, with the Lewis structure, see that there's 1, 2, 3, 4 CH bonds and 1, 2 COH and 1, 2, 3, 4 OH bonds and 1, 2 CO bonds, CO double bonds. You just need to multiply and add and subtract. Practice that. There's 2 problems in here. There's another problem that you can try that'll deal, won't let me show you, but that you should try out. Practice those bond energy problems on pages 20 to 22 and also in this form. One thing you want to know about bond energies is that really they're an approximation. They're a good approximation. It'll really tell us if it's endothermic or exothermic, but also it'll be pretty close to the actual number that we get in an experiment. But you got to understand, not all carbon-carbon bonds, not all bonds are the same. The actual results may vary because of the environment around it. For instance, this carbon-carbon bond has hydrogens all around it, and those are all nonpolar bonds. Right here, this carbon-carbon bond, well, one of the carbons has a bunch of chlorines around it, and those are polar bonds. That's going to change the bond energy in this bond. So these are all approximations, but good approximations. So you guys, we talked about bond breaking and bond forming. Pay attention to that POGIL. Hey, there's even an answer key for that POGIL. Look at the answer key for that POGIL, right? Look at that answer key for that POGIL, and that'll help you understand things. We talked about bond energies and how we can determine that change. Please do your practice. If you want to write up an example problem of your own and show me in here, that's fine. Don't forget to do your reflection here, but most of you will probably be doing this bond energy thing, and you'll see that I give you the Lewis structures and actually just tell you, have you choose and select which answer is correct. So that's really what I need you to be able to do. That's the essential thing for this unit. You guys stay awesome. Have a great week. I appreciate all the stuff that you're doing. I'm so proud of you guys for even just keeping up. These are crazy days, and you're doing crazy good. Thank you.